So a couple things. This number here, wow. I is the square root of -1. That is a 1, believe it or not. Sorry about that. I squared is the square root of -1 squared, which is -1. So typically the imaginary constant I comes from thinking about what do you get when you take the square root of -1. And it's this imaginary number I. And then we have some more stuff. I cubed is I squared times I, which is -1 times I, which is -I. And it goes on. I to the 4th is I squared times I squared, which is -1 times -1, which is 1. And then it just repeats. So every future power of I is just going to be something in the list already. I to the 5th is I to the 4th times I, which is just I. I to the 6th is I to the 4th times I squared, which is -1, and so on. So, right, we have these first 4, I, -1, -I1, and then you just get the pattern repeating. I, -1, -I1, I, -I1, so on and so forth. And this actually is somewhat important when we talk about this pattern, because there's this thing called Euler's formula, which we use some of the time, although not a lot, to deal with something like e to the IT, or more generally, people use theta sometimes. And the formula for this is that e to the IT is equal to cosine of t plus I sine of t. So where does this actually come from? Well, I know this isn't like super 100% important, but I'm just going to show you really quickly where this actually comes from. So there's this thing where we can write out, in fact, apparently we learned something about Taylor polynomials way back in 17a. I feel like that's part of 17a that probably just kind of flies by and like, oh yeah, we saw that, it's gone. So here's a reminder of something you might have seen or not. You might have learned that there's an infinite expansion for sine of x, and it looks like this. X minus x cubed over 3 factorial. You don't need to write this down. You can if you want to, of course. This goes on and on and on, forever and ever and ever. And there's one for cosine of x as well. Cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so on and so on. One way I remember these is that sine is an odd function and all the powers of x are odd. Cosine is an even function and all the powers of x are even. And then there's also one for e to the x, which is e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, et cetera, et cetera, et cetera. And when I look at these, I kind of notice that it kind of, although not exactly, looks like e to the x is a combination of sine and cosine. I could almost just add those together, except the signs would be wrong. If I added sine and cosine, I'd get 1 plus x minus x squared over 2 factorial minus x cubed over 3 factorial, and then so on. So the signs might be right. Well, this formula fixes that. E to the IT. I'm going to replace the x with IT, where I is just this number here, the square root of -1, and t is the variable. So look what happens when I write this. I'm going to get 1 plus, instead of x, I'm going to get IT, then IT squared over 2 factorial, IT cubed over 3 factorial, and so on and so on and so on. Okay, but now I'm going to look at the powers of just I. So when I rewrite this, you get 1, you get I times t. I squared is -1. So I'm going to get minus t squared over 2 factorial. And I cubed is negative I. Minus I times t cubed over 3 factorial. And I to the fourth is just is 1. So I'm just going to get plus t to the fourth over 4 factorial. And I to the fifth is just I. So here's what I would notice. Every odd power of t has a coefficient of I. And every even power of t doesn't. I'm going to break those up. So I'm going to break those up into the odd and the even. So here are the evens. 1 minus t squared over 2 factorial plus t to the fourth over 4 factorial. And the next one would be minus t to the sixth over 6 factorial, etc. And then the other terms are, I'm going to break out the I or factor out the I. I'm left with the t to the first minus t cubed over 3 factorial plus t to the fifth over 5 factorial, etc., etc., etc. But look, that's exactly cosine of t. Right, there's my cosine plus I times sine of t. So if you've been kind of wondering where the heck is this formula coming from, this is where it's actually coming from. This is why we can actually say e to the I times something is cosine of the something plus I sine of the something. It's kind of weird, but it is kind of important. That's why we're talking about it just a little bit. There's also a famous formula that you might have heard of that I feel like I have to tell you because someone should say it once. If you do e to the I pi, it's equal to cosine of pi plus I times sine of pi. The cosine of pi is -1. Sorry, I got the I in there. And sine of pi is 0. So this is considered to be one of the most famous formulas in math because it contains like all the 5 most important numbers. You write it as e to the I pi plus 1 equals 0. Not important at all for right now, but it is a very famous formula that comes from this general formula. Okay, so big deal. We've got this formula for Euler's thing, but that's neither here nor there. We're going to use this when we're finding. So I think he does. There's one problem. I think you actually have to find the general solution of a complex thing. It's kind of a giant pain in the butt, but we're going to come back to that later. So let's talk about this. I want to classify the stability of the equilibrium. And unless someone says otherwise, the equilibrium is just going to be 0, 0 for this system. dx1 dt equals negative x plus 2y, and dx2 dt equals negative 3x minus y. Oh, sorry, yeah. Do this instead. Okay, I really want to stress here. Not being asked to find the general solution. All we're being asked to find is to classify the solution that we're not finding. So we're going to find the eigenvalues. So you can do this in a number of ways. Let's do it kind of the old way. Well, not the old way. We're going to find the determinant of a minus lambda I. And it's an equal the determinant of -1 minus lambda 2, -3, -1 minus lambda. So that's going to be -1 minus lambda times -1 minus lambda minus 2 times -3, which is equal to, let's see, lambda squared plus 2 lambda plus 1 plus 6. Oh, there's an easier way of doing this. That's fine. I don't care. Which is going to be lambda squared plus 2 lambda plus 7. So solving this, it looks like we need to break out the quadratic formula, right? There's definitely no way this factors. It might have been better just to go straight to the trace determinant method. That also would have worked out fine. But quadratic formula, n is going to be equal -2 plus or minus the square root of 2 squared minus 4 times 1 times 7 all over 2, which is going to be -2 plus or minus the square root of, let's see, 4 minus 28 is -24. Do be careful here. It's really, really, it's really, really easy to want that to be positive. You just kind of pretend like you don't see the negative sign and make it positive. It's not. It's definitely a negative in there. This does simplify. It's -2 plus or minus 2 times the square root of -6 all over 2, which then simplifies to -1 plus or minus the square root of -6. Or as we should write this, -1 plus or minus I times root 6. Okay, so we've got our two eigenvalues. Excuse me, sorry. We've got lambda1 equals to -1 plus I root 6. Lambda2 equals to -1 minus I root 6. And I'm going to just say it's actually fairly challenging to write the solution. Defining the eigenvectors is not super easy. It's not, I mean, it's not like super hard. It's still the same process as we would normally use. It's just a little bit uglier. It's still doable, and we're going to do it for one of these. But let's talk about what the general solution would look like. So if we were going to write out the general solution, it would be something like the following. We would have x as a vector equal to c1e to the lambda1t times v1 plus c2e to the lambda2t times v2. And here's what I really want you to see. When we write this, I'm going to actually plug in my eigenvalues, which are up there. Here are my eigenvalues right there. So this is going to look like c1e to the -1 plus I squared root of 6 times t times whatever the eigenvector is, plus c2e to the -1 minus I root 6 times t times whatever the eigenvector is. Okay, so simplifying this just a tiny bit, I'm going to break this apart into the real part and the imaginary part. So this is looking like c1e to the -1 times t, and then t times I times root 6, which I'm going to write as e to the I times t root 6 times v1 plus c2e to the -1 times t, and then -I root 6 times t. Times v2. Okay. So why do we care about writing it this way? Well, here's the deal. This part here, that's the Euler's formula part. So is this part here. And what that's going to do is, well, we could rewrite this. I know it's kind of gross, but this part here is equal to cosine of t times the square root of 6 plus I times sine of t times the square root of 6. And similarly there, this part's going to be cosine of negative t root 6 plus I sine of negative t root 6. But what's that going to do for us? Well, these two things, both this and this, these cause the solution to oscillate. So before, when we talked about our solution, like we talked about what X was doing, what Y was doing. We said, you have X1 of T. Here I used X1 and X2. If you look at what X1 and X2 are doing, previously, we had something like it just like going up or just like going down, but there wasn't any kind of bouncy behavior. But now, because of this portion here, we're going to do something like this. Why is it getting smaller? Well, because of this, right? This e to the negative t, even though this is kind of bouncing around, right, getting bigger and smaller as t gets on and on and on, this part here is just getting smaller and smaller and smaller and smaller and smaller. So as t gets very, very large, this part here is bouncing back and forth between positive and negative numbers, but this part here is just getting super duper small. So it's dampening our bounce. The same idea is true over here. This e to the negative t is going to make this thing smush down as we go on. And this oscillating part here is not going to matter very much. Maybe we're starting here and we're doing something like this. So what the imaginary part of your solution does is it gives you this oscillation. And what the real part does is what it always did. It tells you if both the eigenvalues are negative, you're going to get a stable equilibrium. If both the eigenvalues are positive, it's going to be unstable. And luckily here, you can't have a real part positive and another real part be negative. If your eigenvalues are complex, the real part is always whatever it is. So whenever you have eigenvalues that are complex, they always come in conjugate pairs, meaning whatever A is, it doesn't change. The real part is always the real part. So if the real part's positive, you're going to have an unstable equilibrium. And if the real part's negative, you're going to have a stable equilibrium. It doesn't matter what the imaginary part is, just that there is one. So if there is an imaginary part, that's where you get this oscillation. And if we draw the phase plane, it looks something like this, where we start maybe like over here, and it spirals inward. And because we're oscillating back and forth, but we're still getting smaller and smaller and smaller. And so on. So, sorry. The kind of long story short is that if the real part of the eigenvalues is negative, then we have a stable spiral or an inward spiral. And if the stable part, sorry, if the real part is positive, we have an unstable or outward spiral. I'm sorry, I didn't see this question earlier. Somebody asked how I got 2 square roots of -6. Oh, sure. So looking back here for just a second, the square root of -24, I thought of as the square root of 4 times the square root of -6. And the square root of 4 is 2. And so that became 2 times the square root of -6. So when it comes to classifying, it's not too terrible. All we have to do is figure out if the eigenvalues have a positive real part or a negative real part. I suppose there is one other option. If you're not positive or you're not negative, what are you? There's one number, 0. Yeah. So if the real part is 0, then you have a neutral spiral, which I believe is also called a center, which just circles around and around and around and never goes inward or outward. So I do think it is worth your time, maybe not time, but worth seeing. Sorry, where's my graphing stuff? It's kind of neat to see what this actually looks like. So if we go back and look at our equation, sorry, 1 second. Sorry, here was our equation. We had negative x plus 2y. And we had negative 3x minus y. Graph it. So you can kind of see the spiraliness of it. And if you actually click on a point, oh yeah, look, it's spiraling inwards, right? It's not just a slight curve like we saw last time, right? It actually loops around, right? It's not just one kind of direct inward. You can click all over the place and see, oh yeah, it's very spirally. And we'll talk a little bit later about how to determine the direction of the spiral.
If something is going towards the center, does that make it stable?
Yes.
And if it's going out from it, it's unstable?
That is correct, yeah. So this is definitely a stable spiral. And again, the way we typically determine stability or see that it's stable is if your eigenvalues are both negative if they're real, or if they're complex, the real part is negative. But they really want you to associate, oh yeah, a negative eigenvalue is kind of what goes with stability. And a positive eigenvalue or a positive real part of your complex eigenvalue is what goes with instability. Can you see the eigenvalue thing again? I'm not sure which thing you mean precisely. You mean this part here? Hopefully that's what you wanted. Then this starts with A. It starts with A. Oh, you mean, sorry, I got my cursor on this. Do you mean this thing right here? This little corner part here? Cool. So let's write it all down, just so we all have it. Meaning, here's the big gist. So if you're solving this system, we're solving sorry, this pen is not doing it for me. And I've written this, sorry. Apologies, we're solving this system. The derivative is equal to A times, or as you might usually write it, so if we're solving the system, there's kind of 6 things that can happen. If your eigenvalues are real, you have 3 options. If they're both positive, you have an unstable node, also known as a source. If they're both negative, you have a stable node, also called a sink. And if you have one of each, one positive, one negative, you have a saddle, which is generally considered to be unstable. There are other things, so I should say that you can also have one of them be 0. That's not something we're really going to worry about. And you can also have complex eigenvalues. Lambda equal to A plus or minus B times I. Again, where A is the real part and B is the imaginary part. So there's three things that can happen here. If the real part is greater than 0, meaning if A is greater than 0, we have an unstable spiral, also known as an outward spiral. If the real part is negative, then we have a stable spiral. Or an inward spiral. And lastly, if the real part is equal to 0, then we have a neutral spiral. I feel like the word center doesn't really describe that very well, but it's what they've decided to call it. So that's what it is. So those are the 6 things that can happen. So you can completely classify your equilibria just by knowing the eigenvalues. That's all you need to know if someone says classify your equilibria. You don't need to find the whole solution or any of that. Questions about that? Yeah. So let's look at another one. We'll talk about the direction as well. So the direction can be a little bit confusing. People do like to ask about the direction. So let's classify the stability of the system associated to this matrix. A equal to 2, -5, 2, 1. So let's find the eigenvalues in the other way. Let's use the trace determinant method. So what's my trace here? Thank you. Yeah, it's 3, right? Just 2 plus 1. And my determinant is 2 times 1 minus -5 times 2, which is 2 plus 10, which is 12. Fun fact, if your determinant is negative, you know you have a saddle. I know we talked about that a little bit. I know it's been like almost a whole week we talked about that. I'm just going to remind everybody. If the determinant is negative, you automatically have a saddle. We don't have that here, but I just wanted to say it because it's a really easy thing to know. So let's go ahead and write out the formula for the eigenvalues. It's really just the quadratic formula. And my eigenvalues are going to be the trace plus or minus the square root of the trace squared minus 4 times the determinant over 2. Also, if you look at this, it might help you see why the determinant being negative means you get a saddle. If the determinant's negative, then this part here is positive. And so then you're doing tau plus a number that's bigger than tau and tau minus a number that's bigger than tau. So you get a positive and a negative number. You can't get complex eigenvalues this way if your determinant is negative. Okay, I said enough about that. Let's actually calculate this. It's going to be 3 plus or minus the square root of 3 squared minus 4 times 12 all over 2. That's really lovely. That's going to be 3 plus or minus the square root of 39, a negative 39, which is 3 plus or minus I root 39 over 2. Gross. Not that gross, because we don't have to do anything else with it other than ask the question, is the real part of my eigenvalues positive or negative? Everybody should be able to tell me the answer to that question. You give me a thumbs up for negative and a thumbs down for positive. That's the opposite way. You actually do thumbs up for positive. Give me a thumbs up for positive, a thumbs up for negative. Right, the real part is definitely positive. because this is just 3/2 plus or minus I times the square root of 39 over 2. There's the real part. There's the imaginary part. The imaginary part is just the well, so sometimes people say the imaginary part is just the coefficient. Sometimes they say it's the part with the I included. Either way, you should be like, that's the imaginary part, that's the real part. So the real part's positive, which means we have an unstable spiral. Okay, so now here's the thing. Your spiral could go clockwise or counterclockwise. On my computer at home, I literally have a sticky tab, or what do you call it? Sticky tab. A Post-it note, that's what you call those things. On my computer, it says if the matrix looks like this, it's counterclockwise. If the matrix looks like this, it's clockwise. It's one easy thing, but let me show you the way you should actually think about it before I show you the easy way of doing it. The way you should think about it is not hard. It just takes a little bit of effort. So this system, right, means we're really talking about, okay, dx dt equals 2x minus 5y, and dy dt equals 2x plus y. So what I'm actually going to do is I'm going to pick some points. I often pick points kind of on the axes. So if I pick the point, say, at 1, 0, right there, dx dt is going to equal 2 minus 0. So I'm going 2 to the right, and dy dt is going to equal 2 plus 0. So I'm going 2 up. So I'm going over and I'm going right and up the same amount. So from here, I'm going that way. Okay, let's look at what's happening at 0, 1. So if I plug in 0, 1, dx dt is going to be 0 minus 5. dy dt is going to be 0 plus 1. So I'm going 5 left and 1 up. So at this point here, I'm going a lot more left than I'm going up. I'm probably going kind of like that. And you might pick one more point. Usually, if you, after 2 points, unless they're like specifically going straight to the right or straight up, you can usually kind of tell which way that spiral is going. Am I spiraling clockwise or counterclockwise? It definitely looks like it's counterclockwise. Right? And the idea here is that we're kind of like from here, you're starting off in this direction, and then you're going to go that way, and you're going to go in that direction, and then you're going to keep going kind of around like that. So you can always draw like 2 or 3 or 4 vectors. I either pick points like 0, 1, 1, 0, negative 1, 0, and 0, negative 1. Or sometimes I pick points like 1, 1, and negative 1, 1, and negative 1, negative 1, and 1, negative 1. Something like that can typically give you the directions. Oh, sorry, the papers. How did I get 2 plus 0? Oh, sure. I got 2 plus 0 because I'm plugging in 1 for x and 0 for y. That's how I'm getting 2 plus 0. No, that's all right. I'm sorry. It's hard for, I can't see the board when I'm writing. Let me zoom out a little bit. If it all makes sense, I don't get off so much. Okay, so that's the thoughtful process way of doing it. And if someone asks you the direction of the spiral, this is the work I would encourage you to show, because they're expecting you to be thinking about this way. But here's the shortcut that I've never memorized. It's literally on my computer at home. But I know from this example, so here's the thing. If your matrix looks like this, here's the deal. First of all, the eigenvalues have to be complex to be a spiral. So if we have complex eigenvalues, then it's always true that B and C are opposite signs. I'm not going to prove that to you, but it is true that in a matrix like this, if the eigenvalues ended up being complex, B and C were opposite signs. And here's what's going to be true. It's going to be counterclockwise, like the example we did, if B is negative and C is positive. It's going to be clockwise if the opposite is true. I didn't memorize that fact. I looked at this example, saw that it was counterclockwise, and looked at what C and B were to determine which way it actually worked. But it is true. If you do have complex eigenvalues, you can look at the matrix and the signs of those and determine if it's clockwise or counterclockwise. I still think it's worthwhile and valuable to think about doing this. But if you're looking for a short answer, you can do it that way. It's kind of neat. Honestly, literally what I did when I was teaching this the first time is I Googled, how do you tell if a matrix has a spiral that's clockwise or counterclockwise? And this is one of the things I found. I don't think it's actually in the textbook anywhere, but it's a nice way of being able to. Now, again, if I just give you a matrix, so let's look at another example. Let's say this was our matrix. 1, -2, 3, 4. Is my system of solutions a which way? Is that going to be a counterclockwise spiral? Maybe, if the eigenvalues are complex, but I don't actually know the eigenvalues are complex. So you can't just say it's going to be a this direction spiral until you know the eigenvalues are complex. So before we get going that direction, let's just find the eigenvalues. So let's ask ourselves to classify the solutions here. Or I should say, we're not classifying the solutions, we're classifying the equilibrium. Apologies. It's funny that, so, I mean, I think classify as, and that's this in your homework says analyze the stability, meaning is it stable or is it unstable? And then classify, meaning is it a node or is it a spiral? All right, so let's find the eigenvalues. Which way do we want to do it? Let's do it the same way we did last time. So the trace here is 5. The determinant here is 4 minus 6, which is 10. Okay, so my eigenvalues are going to be 5 plus or minus the square root of 5 squared minus 4 times 1 times 10 all over 2. So we're going to get 5 plus or minus the square root of 25 minus 40 all over 2. And at that point, you can answer the question. Are we stable or unstable? I should back up. I feel like that's not the right question to ask first. Are we a node or are we a spiral? Or are we a saddle? Well, are my eigenvalues real? Or are they complex? Definitely, right? We see a square root of a negative. Oh, they're imaginary, they're complex. So now that we know it's a spiral, then we have to ask ourselves, okay, is it stable or unstable? That has nothing to do with what's over here, it has everything to do with what's over here. So this part here tells us if it's stable or unstable. Since it's positive, it's unstable. Just like if both the eigenvalues were positive, it would be unstable. Right? So this real part being positive or the eigenvalues being positive both lead to instability. It's just one means you have a spiral, one means you have a node. So we have an unstable spiral once again. And once again, it is counterclockwise. Complex, yes. So when I say complex, another word for that is imaginary. So looking at my eigenvalues, now I know I didn't simplify this fully, but I see a square root of a negative. That means there's an imaginary number there. So if I really wanted to, I could say my eigenvalues are 5/2 plus or minus the square root of negative 15 is I times the square root of 15 over 2. That part right there, that's what's leading me to say, oh, this means my eigenvalues are complex because we have an imaginary number there, a square root of a negative. And this part here, the real part, is positive, which means we have instability. Sure. Now going back to the quick way, sure. So the quick way of determining, again, I do recommend drawing it out, but the quick way of determining the direction is if your eigenvalues are imaginary, right? So if they're imaginary, if B is negative, counterclockwise. If B is positive, clockwise. Sorry, do that. That's the fast way of doing it. And again, I'm sure there's some like theory behind this. I have not looked at that. I just literally looked it up. Like, how do you do this the fast way? Okay, that's yeah. So hopefully that is what you wanted there. So what time is it? Okay. I wish I hadn't wasted 20 minutes of your time by being a spaz. Sorry.
So we needed to, when they asked us to get the general solution, that is the last thing we do.
No, so we haven't done that at all today.
Oh.
So let's actually, that's where I was about to go next. So the general solution is a whole nother story. Let's do one that's, do you want to do one with complex eigenvalues? I see. Okay. All right. I knew you guys were saying yes, but I felt like I had to make sure first. Some people, I will say, some teachers kind of totally skip it, which I think is not right, but I didn't want to make you do it if you didn't have to do it. So let's go back and look at this system right here, which I think is the one we dealt with before, but I don't remember. So let's look at this one again. So this is the matrix -1, 2, -3, -1. And we're going to actually write the whole solution to this system of equations. And let's also say we have initial conditions, 2, 0. Writing, so you could also write this out the long way, right? The long way, this is just dx dt equal to -x plus 2y, dy dt equal to -3x minus y, and the initial conditions, x of 0 being 2, y of 0 being 0. And I'm pretty sure this was the system we looked at before. Let me double check so I don't repeat the same work we already did. Can I find it? Maybe, maybe not. There we go. Yeah, totally the same system we did before. So I'll remind everybody, the eigenvalues we found were -1 plus or minus I times the square root of 6, which are not lovely, right? Not my favorite, especially when they're irrational. Here's something worth noticing. When your eigenvalues are complex, you only have to deal with one of them. You can deal with one of them, find its eigenvector, if that's something you're being asked to do, and then the other eigenvalue eigenvector pair are super duper easy to find. I'm going to show you how that works. So let's find the eigenvectors. Let me make sure I don't make any dumb mistakes. Yeah. So let's go ahead and work with lambda1 equal to -1 plus I root 6. And I feel like typically here it is easier to use this equation. So remember, we can find the eigenvector either by doing A times your eigenvector equal to lambda times your eigenvector, or A minus lambda I times your eigenvector equal to 0. They both work, But I do really think, especially when your eigenvalues are kind of nasty, this is the easier way to go. I'll show you both just so you can see they're the same, but I'm going to tell you this is probably the way you want to do it. So let's do that. So I'm going to do A minus lambda times the identity matrix. So in the diagonals, I'm going to be subtracting the eigenvalue -1 plus I root 6. So I have -1 minus -1 plus I root 6, and then 2, and then -3, and then -1 minus -1 plus I root 6 times the eigenvector that I don't know equal to 0, 0. That's my A minus lambda I times B equal to 0. And again, just like before, we're going to use one row, usually the first row. And if you look at this first row, it actually kind of simplifies pretty nicely. I could do a little bit of work before I actually write this out and observe that that's going to be a -1 minus -1 is 0. And then minus I root 6 is minus I root 6. So this actually does simplify a little bit to the following matrix. I would always encourage you to make the choice that makes it easiest to solve for y. Because sometimes people like to ask about the eigenline where you want y equals something, which is not the case here. Right? You never ask about the eigenline when you're talking about complex eigenvectors. But even though I said that, I still want to make the choice where it's easier to solve for y. That's definitely the first row. If I do -I root 6 times x plus 2 times y, it's going to be 0. And then solving for y, I get 2y equal to positive I root 6 times x. And although you could divide both sides by 2, this is the stage where I actually want to write my eigenvector. My eigenvector here is going to be, x could be 2, and y could be I root 6. You could also solve for x, solve for y, and say y equals I root 6 divided by 2 times x. And then x could be 2 and y could be I root 6. Or x could be 1 and y could be I root 6 over 2, but that seems like not the right choice to make. Yeah. Do I need to show you the other way we could do this to believe that it's the same? Yeah, I should show you. So you could do it this way as well. You could do your matrix A, -1, 2, -3, -1, times the unknown eigenvector equal to the eigenvalue times the unknown eigenvector. And my eigenvalue is -1 plus I root 6. Well, look, if we do the first row again, I'm going to get -1 times x plus 2 times y equals x times the eigenvalue. And hopefully you guys can see that this is just the same equation, because I have a -x here and a -x there. Those cancel out and end up with 2y equal to x times I root 6. And that's the same equation I have right there. So they really do result in the same thing. I'll give you guys a moment to look at that before I say more words. So I found one eigenvalue and one eigenvector. So I have λ1 equal to -1 plus I root 6. And the associated eigenvector is 2 I root 6. And now here's the good news. λ2 and the eigenvector associated with it are super easy to deal with. Whenever you change the sign of the imaginary part, you change the sign of the imaginary part. Meaning The associated eigenvector is literally the same eigenvector, but any imaginary parts have the opposite sign. That's it. I can show you all the work if you want. I'm not really going to show you all the work. Watch this. We go back up here. I could have, instead of using negative I plus root 6, I could have done negative 1 minus I root 6. Which would have made this a plus I root 6, plus I root 6, which would have made this a plus I root 6, which would have made this a minus I root 6, which would have been, I could have picked x equal to 2 and y equal to minus I root 6. I really can't stress enough. If you change the sign of the imaginary part, it just changes the sign of the imaginary part in your eigenvector. So you don't actually have to do any extra work. So just for example, I don't think you need to show that work on a test. I really don't. But just for example, let's pretend that I had some eigenvalues. Let's say they were lambda equal to -3 plus or minus 4i. I'm just making stuff up. And let's say we found the first eigenvector to be 2 plus I and -3i. Then I know automatically that my second eigenvector is going to be 2 minus I positive 3i. The real parts stay the same. The imaginary parts change signs. So I just want to make sure everyone knows you're not like changing the entire sign of the thing. You're just changing the signs of the imaginary parts. It's kind of cool. Time is okay, 56. So here's the less fun part. Yeah. So let me back up a little bit, because here's what the solution looks like. So the general solution, when we have imaginary eigenvalues, looks like the following. X is a vector is equal to K1E. Oh, sorry, thank you. Sorry, I'm way off today. E to the AT times the real part of cosine of BT plus I sine of BT times the vector V. But the real part is just this. And then we're going to add on another constant times e to the AT times the imaginary part of the same thing, cosine of BT plus I sine of BT times V, which is just going to be that. I forgot the plus sign there. So in this particular example, here's what we've got. And I should maybe say a few more things here, right? We are thinking, I should say, this is when your eigenvalues are A plus or minus BI. So A is the real part of the eigenvalue and B is the imaginary part of the eigenvalue. Okay, so here's what this looks like. It looks gross. It's going to be cosine of BT plus I sine of BT times V1, which is going to be cosine of the square root of 6t plus I sine of the square root of 6 times t times the eigenvector, which is 2I root 6. Ugh. So that's going to be, as a vector, 2 cosine of root 6t plus 2I sine of root 6t. And then the bottom part is going to be I root 6 times cosine of root 6t plus I root 6 times I. What's I times I? Right, it's -1. I squared is -1. So it's really plus -1 times root 6 times sine of root 6t. The reason I want to make that clear is because when we're writing this whole thing out, which is terrible looking, we want the real parts and the imaginary parts separate. So here's what we're going to do. We're going to say, okay, the real part of this, well, it's that and that. So the real part is 2 cosine of root 6t negative root 6 sine of root 6t. And the imaginary part is this, which is going to be 2I sine of root 6t I root 6 cosine of root 6t. He said I don't actually want the i's in there because we don't include the i's. We're including the imaginary part. We just say that is the coefficient of I. As you can see, this is terrible. Also, I recognize it is 3 o'clock. If you need to go, I totally get it. You need to go. I do feel like I owe you some time. So I'm going to try and finish this for you. But if you want to go, please feel free to go. I will definitely not hold you to be here. There's just a little bit left to do on this. So if you want to see it, you're welcome to stay. So here's what our general solution is going to look like. Let me go back to this for a second here. So we're just trying to throw everything into this terrible looking formula. And our eigenvalues here, if you recall, are -1 plus or minus I root 6. So when I throw everything into this formula, it's going to be, I have to solve for K1 eventually, e to the -t times the real part of all this, which is just that part there. I know just that. And then K2 times e, to the -at, sorry, to the -t, times the imaginary part of this, which is just that part there. Whew. And then finally, we're going to plug in the initial conditions. Why did I write just? Oh, okay. So good question. Someone asked why did I write just this? The real part of all of this is just the cosine of bt times the vector v. And the imaginary part of all of this is just this. It really doesn't even include the I there. It's just the I sine of bt without the I. It's just the sine of bt times the vector v. So that's why I wrote just this. It's because just those parts are the real and the imaginary parts there. We plug in our initial conditions, which I know we might have forgotten by now. They were x of 0 equal to 2 and y of 0 equal to 0. Might like to see that. That'll allow us to solve for K1 and K2. So I'm going to have 2, 0 equal to K1 e to the 0 times cosine of 0 is 1, sine of 0 is 0. So I'm going to get 2 times 1 over negative root 6 times 0 plus K2 times e to the 0 times sine of 0 is 0, cosine of 0 is 1. So here's what I've got, and this is one happens to turn out nicely, like the problem I think I saw someone working on earlier. Can anyone tell me what K1 has to be? It's a nice number. It's not something terrible. K1 has to be 1. K2 has to be 0. And if K1's 1, then 2, 0 equals 2, 0, and I don't want any of this here. And the problem I saw someone working on definitely had the same sort of thing where one of them was like 1 and one of them was 0, which is nice. Okay, so finally, we can say that our final solution is K1 is going to be 1, K2 is going to be 0. So actually, I can probably put it in here. Our final solution is that we get e to the negative t times 2 cosine of root 6t negative root 6 sine of root 6t. Or if you wanted to write them out individually, x of t would be e to the negative t times 2 cosine of root 6t, and y of t would be, sorry, my t, that should just be an e to the negative t. Sorry about that. Y of t would be e to the negative t times the negative square root of 6 times sine of root 6t. That would be your your particular solution to this terrible linear system of equations. But that's, so it's a lot of work, and more often than not, you're not going to be asked to do this general or particular solution for a system of linear equations that have complex eigenvalues and eigenvectors. But if you had to, this is the lengthy process to do it. Next time, when I come to class on time, like the normal person should and would. Sorry, I don't know. I had someone downstairs before that, and then at a meeting, and it ended at 1:30. I was just like, oh, I don't have class till 2. Let me do a few things. And then it's like, oh, wait, no, I just be here. So anyway, enough making excuses. I wasn't here. I'm sorry. Next time we can do another example like this if you guys want to. We definitely can. It's challenging, but we definitely can. And then we'll do some other stuff. How do we get cosine of the square root of 6t? So just to be clear, the t is not inside the square root. But the way we got that was way back here, right? So we used this formula that we didn't derive. We just said this is the formula for the general solution if you have imaginary eigenvalues. And the cosine of square root of 6t comes from the fact that this part here is this b value here. Right, the b value is the imaginary part of the eigenvalue, and the a value is the real part of the eigenvalue. That's what's happening there. And I could say a few more words about that. What's really kind of happening is we're just using the formula. We're using the fact that the solution is k1 e to the lambda 1 t v1 plus k2 e to the lambda 2 t v2. It's just that for these problems, e to the lambda 1 t is e to the a plus bi times t, and that becomes e to the at times e to the bit, and that's where we then use Euler's formula and say, oh, that's e to the at times cosine of bt plus I sine of bt. That's where that's actually coming from. So the fact that a plus bi equals -1 plus or minus the square root of 6 times I. Oh yeah, that's my a. That's my b. That's where that's. Hopefully that makes a little more sense.